Hello everyone, and welcome to today's webinar, which is brought to you by Bettersize Instruments in partnership with AZOM and AZO Network, and is titled Advancing Battery Performance Through Particle Size and Shape Analysis. Big thank you to the team at Bettersize for making this event possible, to you and the audience for joining us from across the world. We're going to get started in just a few moments, but before we do, we have a few points about how to get the most out of your experience today. So firstly, the event is being recorded. We'll be sharing the on-demand link with you within the next 24 hours. So if you enjoy what you see, or you have a colleague or peer who might also benefit from seeing the content as well, then please do share that recording with them when you get that email. If you experience any technical issues today, they are normally resolved by refreshing your browser. But if this doesn't work, then send a message using the Q&A box and our backend team will get you back up and running as soon as possible. Today's webinar will run as 3 parts, 2 presentations and an audience Q&A session. We're delighted to be joined first by Dr. Beverly Barnum, Senior Application Scientist at Bettersize Instruments. She received her Bachelor of Science degree in Chemistry from California State University and earned a PhD in Inorganic Chemistry from the University of Pennsylvania. Recognized for innovative problem solving, Dr. Barnum is a highly accomplished scientist committed to advancing technological solutions. Joining Dr. Barnum is Weichen Gan. Weichen is an application scientist at Bettersize Instruments. He received his Bachelor's of Science degree in Material Science and Engineering from Harbin Institute of Technology and earned a Master's in Material Science and Engineering from the University of Florida. Since joining Bettersize, Weichen has been focusing on the characterization of the physical properties of inorganic materials and helps provide relevant solutions. Big welcome to you both today. As I mentioned, there will be a Q&A session following the presentations, so please send those in as and when they come to mind using the Q&A box, which you can find on the right-hand side of your screen. You'll also find some handouts on the left-hand side, which you can download at any time. And if you want to change the size of any of the modules you can see on your screen, then you should see a full screen mode to the top right corner of your presentation window. Quick note that if you are watching this back on demand, you can still ask your questions, but you will receive an answer to your question via email. Right, I'm delighted to now welcome Dr. Barnum to get things started. Dr. Barnum, over to you.
Thank you for the kind introduction. Hello, everyone. Today I'm going to talk to you about batteries, specifically rechargeable lithium-ion batteries, and the importance of particle size distribution, and particle shape within these batteries. What are lithium-ion batteries? Our modern tech life includes rechargeable batteries everywhere, commonly used in flashlights, cell phones, cordless vacuums, power tools, electric vehicles. You're most likely watching this webinar on a laptop run on lithium batteries right now. So what is a lithium-ion battery? And what are they made of and how do they work? Lithium-ion batteries, like all batteries, store energy and convert it to electricity when needed. A lithium-ion battery generates electricity through chemical reactions of lithium. If we look at this diagram, we can see the key components of the lithium-ion battery. On the right, we have the anode. It stores and releases lithium ions to the cathode in a process called intercalation, which is the reversible inclusion of the ions into compounds with layered structures. In this case, the anode is composed of graphite powder, and we also have a copper current collector on the right. On the left, we see the positive electrode, the cathode. This is typically a lithium-based metal oxide or phosphate, and on the end, we see an aluminum current collector. The cathode is the source of lithium ions and determines the capacity and voltage of the battery. Surrounding everything in here you see is the electrolyte medium. There's a pool of a liquid electrolyte here. This electrolyte is a component that has many roles, primarily ion conduction. The electrolyte carries positively charged lithium ions through the separator and transfers these ions back and forth between the 2 electrodes, causing the battery to charge and discharge. Common electrolytes are composed of salts, solvents, and additives, such as lithium hexafluorophosphate, lithium perchlorate, lithium tetrafluoroborate, lithium hexafluoroarsenate. These are dissolved in organic carbonates with carboxylic ester additives to help dissolve the lithium salt. In the middle of this diagram, you see the separator. This is a physical barrier. a thin porous membrane that keeps the cathode and anode separated. This blocks the flow of electrons inside the battery, while still enabling the lithium ions to move between the electrodes. Today we use synthetic resin materials like polyethylene and polypropylene. So what's going on? How does this work? Internally, the lithium ions, which are these little red dots in this image, move between the electrodes with the conductive electrolyte. The separator prevents a short between the electrodes. So the ions move, but the electrons do not move through the separator. When the battery is discharging, when it's in use, electrons flow through the external circuit, moving from the anode to the cathode, and this provides power. Simultaneously, the lithium ions are released by the anode and received by the cathode using the electrolyte train. When the battery is being recharged, we externally apply an electrical current to reverse the flow of lithium ions. Internally, that means the cathode releases the lithium ions and they move through the electrolyte through the separator and the anode receives them. Briefly, I want to share that solid-state battery image. This operates on the same principles as a lithium-ion battery, but with a few key differences. Solid-state batteries use solid electrolytes instead of the liquid electrolytes, and these are comprised of sulfides or oxides typically. These perform better in terms of stability, safety, and thermal conductivity, and they do not leak or evaporate, so they're inherently safer. There's a slight difference in the electrode materials, where the anode, the negative electrode materials in these solid-state batteries often include metallic lithium or lithium titanate or silicon-based materials. And this allows the energy density of solid-state batteries to be greatly increased. There's differences in terms of the interface characteristics, since now the interface contact of solid-state batteries is no longer solid to liquid, but it is solid to solid contact. And this means that there's a smaller contact area and higher interface resistance. These solid-state batteries, as new tech, have negative cost differences. However, the gains are energy density, charging speed, and thermal stability. Current challenges involve optimizing electrolyte compositions, developing new solid-like electrolyte materials with enhanced stability and conductivity. So I've mentioned a lot of the materials that are used in lithium-ion batteries. And they include lithium, graphite, cobalt, nickel, manganese. These metals are used in the battery's electrodes and electrolyte components. But we can't use metals as metals all the time. As stated, a lithium-ion battery generates electricity through chemical reactions of lithium. But elemental lithium is unstable, so we use active materials can undergo reversible lithium-ion intercalation during battery charge and discharge cycles. The lithium-ion battery cathodes are comprised of active materials plus additives such as binders and carbon black to enhance the contact between the particles. These each offer distinct advantages in terms of energy density, cost, and safety. The most commonly used materials for cathodes include a variety of lithium metal oxides. These metals provide a stable framework for lithium ions to move in and out of during charge and discharge cycles. Just like the cathode, the anode substrate is also coated with active material. The anode's active material performs the role of enabling current to flow through the external circuit while allowing reversible absorption of lithium ions released from the cathode. Commonly used graphite is innately electronically conductive. It has a stable structure, low electrical chemical reactivity. It's able to store many lithium ions, and all at a low cost. If we examine some of these materials used in lithium-ion battery manufacturing, and here we have some SEM images, there are a few things to note. Here, the lithium nickel manganese cobalt oxide, you can see that we have a rather large particle size distribution, where we have round materials, but they're all of various diameters. If we look at the lithium iron phosphate image on the right, we can note that it has a non-smooth surface. On the lower left, we see graphite, and it's comprised of some very irregular shapes, as you can see. And of course, carbon nanotubes are non-spherical. So in real life, particle shapes are irregular, and this creates challenges when trying to measure them using different measurement methods. So I'd like to take a step back because I mentioned the word particle. Particle, what is a particle? Particle is a small, discrete unit of matter with defined physical properties such as size, shape, and composition. Particles can exist in various forms, including solids, liquids, and gases. How do we measure particle size? Common techniques include sieving, imaging, microscopy, sedimentation, resistance, laser diffraction, dynamic light scattering, photoresist, ventilation methods, X-ray scattering, etc. And there are pros and cons to all these methods. However, only a perfectly spherical, non-porous, smooth, non-charged, monodispersed particle would give the same results used when we use all these techniques. However, the most common measuring techniques are sieve, laser diffraction, and dynamic light scattering. We measure particle size in terms of equivalent diameter. This is commonly used when sizing particles because it provides a single representative value that simplifies the characterization of particle size distributions. We can see this image on the left is an expression of the equivalent spherical diameter of a particle. And we see the image on the right is a volume equivalent diameter expression for a non-spherical particle, expressed as a spherical particle. What is particle size distribution? That's PSD. This refers to the statistical distribution of particle sizes in a sample. And this provides information about the range of particle sizes present, the ratio of particle sizes within each size range, and the distribution pattern of particle sizes across the sample. Particle size distribution is crucial in lithium-ion battery manufacturing due to its direct impact on the performance, the efficiency, and the safety of the batteries. The key to efficient lithium-ion batteries lies in the effective contact between the lithium-ion-rich electrolyte and the active material particles in the electrode. The particle properties of the electrode materials affect the diffusion path, diffusion resistance, the contact area with the active material, the electrochemical performance, and the energy density of batteries. To achieve good performance of lithium-ion batteries, it is not only necessary to focus on the modification of materials, but also to balance the properties of electrode material particles. And these properties that we should consider are size, size distribution, and shape. These particle properties have significant impact on the battery performance due to their role in determining the efficiency, capacity, cycle life, and safety of the battery. And here's how various particle properties influence battery performance. Particle size affects electrode packing density, surface area, and ion diffusion rates. Smaller particles enhance capacity. However, excessively small particles can lead to increased side reaction and loss of active material, affecting battery stability and cycle life. Particle size distribution. If we control the particle size distribution, we can ensure a uniform electrode packing and efficient ion transport. And this would optimize battery performance and energy density. However, having a relatively broad particle size distribution combined with spherical shape of electrode particles can help to obtain a higher specific charge capacity and higher energy density. So it is important to consider the benefits and the adverse effects in real applications and flexibly adjust the particle size and particle size distribution of electrode materials to meet the requirements for different application scenarios. Particle shape influences electrode packing density, ion diffusion pathways, and mechanical stability. Spherical particles typically pack more densely and evenly, and this promotes uniform ion transport and reduces stress-induced damage during charge and discharge cycles. I briefly want to introduce one other characteristic of these particles. This is zeta potential. What is zeta potential? Zeta potential is a measure of the electric charge surrounding a particle suspended in a liquid medium. So potential is not a property of the particle, rather, property of the system, which is comprised of the particle and the medium. Zeta potential influences battery performance in terms of electrode stability, electrolyte interaction and ion transport, the prevention of side reactions, cathode electrolyte interface stability, and battery safety. We can affect characteristics of lithium-ion battery by balancing particle size. For example, with respect to electrochemical reaction kinetics, smaller particle sizes generally lead to faster lithium-ion diffusion and shorter diffusion pathways within the electrode material. This results in improved electrochemical reaction kinetics, including faster lithium intercalation and deintercalation rates, and as a result, batteries with smaller particle sizes typically exhibit higher charge-discharge rates and improved power performance. However, smaller particle size can increase agglomeration formation, and this leads to a decrease of the electron conductivity and solid phase diffusion coefficient, increasing resistance, and this ultimately affects the capacity and discharge performance of the battery. Size also affects capacity and cycling stability and electrode packing density. Therefore, optimizing particle size achieves optimal performance in lithium-ion batteries. Particle shape significantly influences the performance of lithium-ion batteries in several ways. In terms of the electrode packing density, different particle shapes affect how closely these particles can pack together in the electrode. Higher packing density, typically achieved with spherical particles, allows for more efficient use of space within the electrode. And this can lead to higher active material loading and thus higher energy density in the battery. In terms of ion diffusion pathways, particle shape impacts the pathways available for the lithium ions to move in the electrode materials. Shapes like flakes or platelets may offer more accessible surfaces and shorter diffusion paths for ions compared to spherical particles, which can enhance the battery's rate capability by allowing faster ion transport through the charge and discharge. However, other shapes can cause a strain path, and this would have a negative effect on the charge and discharge cycle. Electrical conductivity is affected by the shape of particles and the contact resistance between the particles with the current collector. Shapes that promote good electrical contact, such as flakes with high aspect ratios or other well-oriented structures, can improve the overall efficiency of electron transfer within the electrode. And this contributes to better battery performance, especially in terms of power output and efficiency. For mechanical stability, certain shapes, particularly flakes or fibers, can enhance the mechanical strength and flexibility of the electrode structure. And this reduces the risk of electrode cracking or degradation during repeated charge and discharge cycles. And this improves the battery longevity and reliability. In terms of cycling stability and lifetime, particle shape impacts how effectively the electrode material accommodates volume changes during charge and discharge cycles. Shapes that minimize these stress concentrations and maintain structural integrity over multiple cycles can enhance the battery's cycling stability and extend its operational lifetime. So, careful consideration of a particle shape allows for the optimization of these factors to achieve batteries with improved energy density, power output, durability, and overall performance. One key to battery production lies in the consistency of the electrode slurry, where control of the density and viscosity is vital. Particle size and shape affect slurries' rheological properties. Generally, smaller sized particles typically lead to lower viscosity slurries, and irregular shapes can result in higher viscosity slurries. In terms of coating uniformity, small sized particles produce uniform coatings, which result in electrodes' consistent thickness and electrochemical performance. and spherical shaped particles tend to pack more densely and uniformly. We can affect electrode density and packing efficiency, with smaller particles achieving higher packing densities, and this maximizes utilization of the active materials, therefore the energy density. Certain shapes may enhance packing density or improve the accessibility of the ion diffusion pathways. In terms of electrochemical performance, fine particles provide higher specific surface area, and this facilitates faster ion diffusion and enhances better performance in terms of rate capability and cycle life. Shapes with high aspect ratios, for example, flakes, can offer shorter ion diffusion paths or better electrical contact, and this further improves the electrochemical performance metrics. For mechanical properties, particle size influences the integrity of the electrode, affecting its resistance to mechanical stresses during battery cycling. Certain shapes, like flakes and fibers, can also enhance the flexibility, mechanical stability of the electrode structure, and this reduces the risk of cracking or delamination. So, optimizing particle size and shape allows for the development of electrodes with improved energy density, power output, cycling stability, and overall performance. Now, hopefully, you understand a little bit more about lithium-ion batteries and how particle size distributions, and particle shape can influence lithium-ion battery performance. Now that you have the what and the why, I'll hand this conversation over to Weichen to explain how you can perform particle size distribution, and particle shape analysis. Thank you.
Thank you, Beverly, for your comprehensive introduction. Hello, everyone. For the following part, let us focus on how we can handle the particle size and shape. How can we make a measurement of these key parameters of battery performance? We will explore particle size and shape measurements in these aspects, how the measurement works, then the actual use, and what Bettersize offers. This slide illustrates the principle of light diffraction. This method is also known as light scattering since it utilizes the scattering of light which occurs when light interacts with particles. As shown on the left, when light shines on a particle, the light scatters. Scattering is a combination of four phenomena: reflection, attenuation, refraction, and diffraction. Diffracted light will project a pattern on a screen in the form of a series of concentric circles of varying intensity. This pattern is called the 𝗨𝗨𝗃 pattern. If we fix the wavelength of the light, the distance between the particle and the screen, the 𝗨𝗨𝗃 patterns will vary systematically with particle size, as shown in the picture of large particle and small particle cases. One thing that needs to be mentioned is, in the real world, particles of mixed size will form a mixed pattern, also known as spectrum, just like the multiple sizes image shown. On our right is the structure of a typical laser diffraction particle sizer. It is made up of a sample feeding and dispersing system and a measurement system. The measurement includes the collecting process of scattering spectrum and analysis of the spectrum. The result would be in the form of particle size distribution, contents of particles in specific particle size range. In general, laser diffraction technology provides a wide dynamic range, which means it is appropriate for a range of applications. As my colleague Dr. Barnum shared in her speech, particle materials are in micron range, and the laser diffraction method works perfectly in that range. Meanwhile, the test efficiency is good, making it possible to monitor some particle size changes and save some value time for taking some action. Also, the results come with good quality. a large amount of particles can be measured with a single test, thus ensuring a good representativity of results. Now we know how laser diffraction technology helps us measure particle size. But how do we make measurements of the shape of micron-sized particles? The answer is the image analysis technology. The working process of image particle size and shape analyzers is to take a photo of particles and then analyze particle size and shape with that photo. To clearly observing the particles without distortion, usually people will use an optical microscope to magnify particle images. With each particle image, we can associate several distinct attributes to describe important aspects of the particle, such as circularity is how round the particle is, and the aspect ratio for comparing the difference between particle length and width. Compared with laser diffraction, image analysis is a straightforward method. It is easy to understand and easy to operate. It is widely trusted by a variety of industries. Of course, the battery industry is included. During the measurement process, the image analysis technology measures each particle's size and shape first, and then compiles statistics on each attribute. In this way, the high resolution of the result is ensured. Also, the measurement of each particle provides us the possibility to do a comprehensive analysis combining the size and shape of every single particle. The picture on our right is a scatter plot, of which the vertical axis is particle shape and the horizontal axis is the particle size. With the plot, it is easy to pick out large but circular ones and calculate their content, or we can visualize what the main population looks like. Are they large enough or are they rounded enough? Lastly, since the resolution is down to single particles, the image analysis is sensitive to oversized particles, even if they are in small numbers like 1 in 1,000. As mentioned earlier, both the laser diffraction and image analysis method provides particle size or shape distribution as results. In the real battery, particles are of different sizes and shapes, but every particle matters. Single particle size measurement is crucial, and understanding the size distribution of a group of particles is also essential. The distribution can help us understand the size or shape of a group of particles in both quantitative and qualitative ways. Need to ensure LFP particles in a battery are of uniform size? Particle size distribution can help. Need to ensure the rounding process of graphite is making effect? Particle shape distribution can help. Need to evaluate different processing parameters like extending grinding time? Particle size and shape distribution can help. As my colleague Dr. Barnum discussed in the first part, it is the particle size or shape distribution help us understand the relationship between particle properties and battery performances. Okay, now we understand how to measure particle size and shape through laser diffraction and image analysis methods. Now, let's see how Bettersize combines them together and helps measurement both particle size and shape distribution within one test. We are thrilled to introduce the Bettersizer S3+ Particle Size and Shape Analyzer. It is a 2-in-1 system combining laser diffraction technology with image analysis technology. Thus, we can utilize both methods to best understand the size and shape distribution of particles. For the laser diffraction part, the Bettersizer S3+ is equipped with a Bettersize patented dual lens and oblique incidence system, 𝗨𝗨𝗽𝗁 system, to ensure the accuracy of measurements, even for the finest particles down to 0.01 microns. For the image analysis part, the Bettersizer S3+ has a dual camera system to rapidly and accurately capture flowing particles. To help better utilize the unique design of Bettersize S3+, making the best performance, and to do measurements more easily, we provided 2 dispersion units and 1 optional auto-sampler for it. If the particles are insoluble in water and comes in a large quantity, such as some lithium iron phosphate LFP materials, then BT803 can be the most ideal choice. It is a fully automated dispersion module with automated test functions. As for samples dispersed in organic solvents, there is BT80N works perfectly in this scenario. It is okay to dilute the sample with NMP in the BT80N and then do the test with Bettersizer S3+. To make the size and shape measurement of suspensions easier, the BT860 auto-sampler is here to help. It can hold up to 60 samples and only 1 click is needed to do those 60 measurements. As mentioned earlier, the Bettersizer S3+ combines laser diffraction and dynamic image analysis in one instrument. Thus, it can measure the size and shape of particles from 0.01 micron to 3,500 microns. Benefited from image analysis, it has exceptional sensitivity for oversized particles. With Bettersize's patented Deloy system, the Bettersizer S3+ also expanded the lower limit of ultrafine particle detection. The unsurpassed resolution and its sensitivity for either ultrafine particles or oversized particles make it the most powerful size and shape analyzer for enthusiastic researchers who conduct top scientific research. The hardware and design of Bettersizer S3+ are just some of its outstanding aspects. The Bettersizer software provides an easy handle for managing the whole test process. Starting with an intuitive interface, the software is designed to guide you through a highly automated test process. During the test process, there is a real-time mode showing the real-time particle size distribution, which helps to check the measurement conditions. After the results are there, the Bettersizer software provides an automatic cleaning function to flush away all the residuals. The cleaning process can be tailored to best match the sample. Worried about the data security? Bettersizer software also provides an auto backup function to secure the data. Both test results and test SOPs can be backed up. With satisfying results, Bettersizer software can fill them into customizable reports. The software can help export the report in different formats and with a variety of templates. But it is also possible to have your own template. Before we take a look at the Bettersize customizable report, let's see how a measurement can be made. Here we can take graphite as our example. As we know, it is a kind of black dry powder, not soluble in water. But one thing we should consider is that most graphite samples are not so wettable. This means if we directly pour dry powders into water, or vice versa, they will float on water but not forming a suspension. To do the test in ideal dispersion status, we should do some pre-dispersions, such as adding diluted surfactant or using external ultrasonication. In the end, a thick suspension would be dropped into the dispersion module BT803, then being stirred and ultrasonicated there. Well-dispersed particle suspension will circulate between the dispersion module and the Bettersizer S3+ main unit. Data collected will be analyzed in Bettersizer software. After a test, now the data is collected. Here we have unprocessed graphite tested with Bettersize S3+ and got a particle size report in this way. The default particle size report generated by Bettersize S3+ includes first, basic information of sample, like the sample name, operator, and test date. Second, particle size typical values. The number here means particle size in accordance with content percentage, such as D10 of this sample is 11.63 microns, which means 10% of this sample is smaller than 11.63 microns. Also, to present particle size distribution, there is distribution curve, table, and a simplified table. To check the shape information, we also provide another report. Different from particle size report, on this shape report there is particle shape information. Those are average value of the whole sample. The shape report can provide a particle gallery to give the reader an actual way to evaluate the shape of particles. This sample is an unprocessed one, so you will see some particles with irregular shapes. So, we have walked through how to make measurements with Bettersize S3+. The next part will be some practical cases of using Bettersize S3+ or other Bettersizers to analyze particle size and shape in the battery industry. The first case will be on the topic of particle size and shape. As my colleague Dr. Barnum shared in her speech, both particle size and shape of anode particles are related to battery performance. The most ideal situation will be for all the particles to have a uniform size and rounded shape. But in the actual world, it would be hard to round the graphite particles to such a round shape, whether natural graphite samples or synthesized ones. So, people would take the situation in the middle. Thus, a relatively even size and relatively rounded shape would be fine. The picture shown on our right shares how a real graphite sample looks like. They do not have sharp edges, but those graphite particles are not in perfect spherical shape either. In a Bettersize application lab, 3 samples were measured. They are of different sizes, a bit similar shape, and different tap densities. As we can tell from the data, sample B is not of the largest size or smallest, but it has the largest scalarity value. This means the particle of sample B is the roundest among 3 samples, and a more important thing is the tap density of sample B is the largest. That indicates sample B will help maximize the energy density of the battery. So, despite the particle size comparison, sample B would be the mostly welcomed one among these graphite samples. More details and insights are written in our application note, including how the sample is being measured and why the tap density should be maximized. Please search over Bettersize knowledge base for this application note. Here is another sample of using Bettersize S3+ to help evaluate the quality of particles. But this time, we are making measurements of processing LFP materials. The LFP materials are also insoluble in water, but the size distribution of LFP particles varies according to their preparation process, such as this sample we measured in the Bettersizer lab. The particle size distribution curve shows a bimodal dispersion, which means the sample includes 2 groups of particles of different sizes. Thanks to the image analysis part of Bettersizer S3+, we can easily find out what is the larger volume particles which cause the actual peak on the PSD curve. Check the single particle gallery of Bettersizer S3+ measurement results. We can find they are oversized LFP particles and some agglomerations. to eliminate oversized LFP particles, improvements in grinding or other processing are required. As for agglomerates, changing dispersion settings such as using a higher power of ultrasonication can be helpful. Agglomerates, oversized particles, and air bubbles can cause similar results, that is the bimodal distribution. And the peak in the red box indicates some large particles. But what are they? Real-time images of Bettersizer S3+ can clearly identify the cause with particle images, and thus help us locate the problem. We can observe particles in real time with high-speed CCD cameras inside Bettersizer S3+, and the imaging methods are by their nature highly sensitive to small amounts of extra-large particles. This is an application case of anode material rounding process. As the picture on our left shows, the graphite needs to be rounded, but the process needs to be stopped at a suitable point, otherwise the over-rounding will cause waste of cost and time. For some country or region, the standard value is average circularity larger than 0.9. The dynamic image analysis can help accelerate circularity measurements with its high efficient and provide us with a robust way to measure particle circularity. This method is fully in accordance with the standard also. From particle shape distribution on our right, we can find that the sample 1, after processing, the particles are more rounded than sample 2, which is unprocessed. We have a lot of successful stories with different customers from the battery industry. Bettersize is glad to help those big names improve their product performance, like the Fine Dreams battery of BYD Group, LG New Energy, or PU Lead, which is a famous cathode material provider. Of course, more stories is ongoing or going to happen. We are more than happy to help charging your battery for a better future. Now we have come to the end of this sharing, and here is a summary. We have gone through how laser diffraction and image analysis, two important particle size and shape analysis technologies. Then, we have seen a combination of laser diffraction and image analysis, the Bettersizer S3+. And in the end, we went through some Bettersize case studies. Well, if you are still wondering how Bettersize can help you, Bettersize is now providing a free sample testing service. Please check our website and send us your samples. We hope that this sharing can help you with improving the battery performance. Thank you.
All right, thank you very much, Weichen again. Thank you very much, Dr. Barnum. We're going to now start the Q&A. Just before we do, Weichen just mentioned about the free sample. You can find the link that should be popping up on your screen any second now, and you can click that. You can click that and you can find out information about how you can send your sample into the team at Bettersize. So please do take a look at that before you leave today. All right, let's get started with the Q&A. Dr. Barnum, if I come to you first. This one's asking, what role does particle size play in the thermal stability of lithium-ion batteries?
Thank you. Particle size plays a crucial role in the thermal stability of lithium-ion batteries. Smaller particles can lead to higher surface area. This may increase the reactivity and the heat generation during the charge and discharge cycles. And this can potentially lead to thermal runaway if we don't manage this correctly. Conversely, if we have larger particles, this could exhibit improved thermal stability. However, this would be offset by limits of the battery capacity and the charge rate. So optimizing particle size is essential to balance safety and performance.
Wonderful. The next one is in two parts. Dr. Barnum, perhaps if you take the first part and then Weichen, if you take the second part. They're asking, how does PDI influence the performance and safety of lithium-ion batteries? And then the second part is, what specific methods are most effective for analyzing this parameter?
So, particle size distribution impacts the performance and safety of the lithium-ion batteries in a few ways. So, smaller particles can enhance, again, like I said, the surface area, and this can be applied to the electrochemical reactions, which lead, again, to higher capacity and faster charge and discharge cycles. However, if the particles are too small, this leads to issues, as I mentioned before, like increased resistance and instability. So, effective methods would be answered by Weichen.
Okay, so as we just discussed, so PDI it is like a polydisperse index. So actually, every single method that can measure the distribution of particle size can help us. I mean, can provide us the PDI. So right now, the most widely used technology may be the laser diffraction, but still image analysis or a combination of them can also help us to make measurement of PDI of samples.
Superb. This next one's also in two parts. And again, Dr. Barnum, if you take the first part, Weichen, if you want to take the second. The first part is asking, you referred to NMP, can the Bettersize S3 plus be applicable to NMP, and particles are in the nanometer range? And the second part, how does laser diffraction compare to other sizing techniques like sieving and grind gauge?
So NMP stands for N-methyl-2-pyrrolidone, and this is a polar aprotic solvent. This is commonly used in lithium-ion battery production because it has excellent solvent properties as opposed to, that's not water. And it is able to dissolve a wide range of substances, including polymers and salts. And so this is used frequently in the slurries to make electrodes. So it is valued for its ability to facilitate these chemical reactions, and also it has a relatively high boiling point. But it's also subject to high scrutiny by regulations for its potential health effects. So various techniques such as DLS and LD are well suited for measuring, and we can use NMT as solvents in these, and this can help provide accurate size distributions. So Weichen can go on and can discuss this a little further.
Yeah, all right, thank you. So regarding to different comparing laser diffraction results with different methods, that is a really good question, and actually we are very commonly asked by that question. So the particle size, one thing we need to mention is the particle size results measured by different technologies. It may varies, but they are in accordance with different physical property of particles. So if we do tend to see differences in the results that got between like different methods like laser diffraction and like or sieving or grinding gauge, that doesn't mean a specified technique is good or bad. It depends on the demanding and actual situation of the particle size measurement. So we can take some unprocessed like flake-like graphite as an example here. Although they may very small in volume, but since they are very thin flakes, so those flakes are not so easy to pass the sieve openings. So they may slightly oversize the material in this situation. And we will see the differences between the result of sieving and the laser diffraction. Also, it worth mentioning that the time efficiency and result repeatability of laser diffraction are slightly better. But still, sieving can be a good choice in some specific occasions, especially when you are looking for like physically picking out oversized particles. Another technique you mentioned is grind gauge. It is an efficient way and simple way to check particle size of sticky slurries, and it is widely used in the industry also. It is pretty sensitive to oversized particles, but it doesn't provide a good particle size distribution information. So in other words, the grinding gauge, it is a good quantitative analysis, but not, it is not a good qualitative analysis, but not ideal as laser diffraction when a quantitative analysis is needed. So for this very commonly asked question, when we talk about laser diffraction, we are more than happy to help you to relate results of different methods, since they are not correct or wrong. They are just describing this different aspect of particles. So comparing them and relate them together can help you to develop understanding of your materials. Thank you.
Superb. Thank you, Weichen. And this next one's probably best for you as well. It's asking, what would you say is a typical time for one of the measurements?
So yeah, that is another very commonly asked question. So the test time, okay. The test time actually for laser diffraction, it depends on the sample dispersion state and time cost on dispersion process. So assuming we are testing some particles easy to be agglomerated, like some lithium iron phosphate samples, the whole process may take like about 3 to 5 minutes of ultrasonication and stirring in Bettersize S3+ to make the sample, the particles fully dispersed. But for some particles easy to be dispersed, like lithium nickel manganese cobalt oxides, the NMC materials, 30 seconds of stirring are enough to get them well prepared. So in a nutshell, the time of measured sample, it really depends on how agglomerated it is. But from our experience, the test can be done within a couple of minutes.
Perfect. We've got lots more questions. Just a reminder, if there isn't time to answer your question today, we'll pass them all on to Dr. Barnum and Weichen, and they can follow up with you via email at a later date. A couple of other reminders that on the left-hand side of your screen, you should see 5 handouts, an application note that Weichen referenced during his presentation, a video, the slides, and one other item as well. So do download those before you leave the webinar. If you are watching this back on YouTube, we'll put links below in the comments, and you can download them from there. This next one, Dr. Barnum, if I come back to you, is asking, what is the optimum particle size? If too small, is this disadvantageous?
I think I had mentioned before with some of the earlier questions about there's a balance between size and functionality, basically, and depending on the end use of the battery, then you have to balance those properties. In addition to that, with safety. So one of the most important things now is safety, which is why we are trending towards solid state batteries. So it truly is a balance between those things and optimizing your energy density along with your recharge properties.
Lovely. And then, which I'll come back to you. For the Bettersize analyzers, what is the minimum sample volume required, and how much fluid is used for each measurement, including any flushes between sample measurements?
So yeah, this is a very actual question. So it depends on which kind of module, dispersion module you are using with Bettersize S3+. So we mentioned earlier in my sharings, there is 2 different types of dispersion module. One is called the BT803, and it will contain up to 600 milliliters of liquids. But still, you can use a little bit less, like 400 milliliters, and it still works perfectly. And about another one is called BT80N, and BT80N is designed for smaller volume, and you will use less. Liquids, like 80 milliliters are working pretty good. And so that really depends on what kind of liquid you're using and what is the sample. But yeah. And another part of question is including any flushes between sample measurements. So usually we can simply calculate it as 𝗨𝗪𝗶𝗴. So For example, if we use 60 milliliters of liquids with BD80N, and then we are going to triple it, so it will be like 180 milliliters of liquids in total, including the test and flush. Thank you.
Perfect. We're getting pretty close to the hour. I think we'll take at least one more question. And just before we do, there is another webinar coming up in September. We're going to put a link to that one on the screen now. Dr. Barnum, perhaps you could just briefly talk a bit about this webinar, who should attend, what's it about, that sort of thing.
Yes, the webinar is called Pushing the Limits. It's pharmaceutical characterization with light scattering. So they'll be applying dynamic light scattering and electrophoretic light scattering to pharmaceuticals. And so they will describe how these techniques can enhance pharmaceutical processes, including drug formulation, stability, delivery, and improve the quality and efficacy of pharmaceuticals. ELS relates to zeta potential, which I had briefly mentioned in my part of the webinar today. And so this will help in terms of help R&D and QC groups with comprehensive pharmaceutical characterizations. And so we look forward to hearing from Dr. Don Miller and Jibin Gao in September with that. Thank you for letting me talk about that.
Fantastic. And yeah, so if you click the link that's on your screen, that webinar is up in 25th of September 25th, an hour later than today, but around about the similar time. So if you are interested, then do register for that, and we'll see you at the end of September. I'm also just putting in the comments a link to the free sample again. So if you missed it earlier, you can click on that and you can find out all the information for sending over your free samples. Just the one more question, I think, Weichen, I'll come to you for this. They're asking, is the software secured by password and audit rail?
Yes, actually, this question is perfectly matched with our next webinar, since the audit rail function, this function, and the password security, they are actually widely used in the pharmaceutical industry. As we both know that the audit trail, the digital log, the FDA 21 CFR Part 11 compliance, they are already implanted. These functions are already implanted in Bettersize software. So you can use audit rail to do the trailing of any movement that you have been done with the Bettersize software, and the software itself can be secured by a password.
Superb. Thank you both very much. I think we'll wrap things up there. We're getting close to the hour. Just a reminder that if you have missed anything, a link with the recording will be in your inboxes by the end of the week. Everything that we've referenced, any links that we've talked about today, we'll make sure in the comments. If you're watching back on YouTube, you can find those as well. If your question hasn't been answered, I know there are a lot of open questions still. We'll pass them on to Dr. Barnum and Weichen, and they can get back to you as soon as they can. Big thank you to you both. Any final thoughts before we wrap things up? No, all good. We've had lots of positive feedback already, so that's always a good sign. Lots of heart emojis coming in. So big thank you to everyone in the audience for joining in from across the world. I appreciate a lot of people will be staying up pretty late to join as well, so thank you to them especially. Wish you all a pleasant rest of the day, and hopefully we'll see you all again very soon. Thank you very much.
Thank you.